Hello, nerds. Tons of you asked for continuing the series. Previously, we learned that the Acer laptop is using WMI to communicate with the hardware. And today, we will try to understand what is WMI and how do we control it. So, what is WMI? WMI stands for Windows Management Instrumentation. It is a set of tools and extensions for the Windows operating system that allows you to manage and monitor a wide range of system resources, including hardware components, software applications, and network settings. WMI provides a standardized way to access and control management information in an enterprise environment. The WMI is part of the ACPI, and ACPI can communicate with hardware. Basically, in era of first computers, users could power off the computer only by pressing a physical button, and it was not possible to turn off the computer with the software. So ACPI have been developed to address such issues. I will attach a link to AKIO TV that explains ACPI with more details, but it's really easy to understand, at least the way the AKIO try to explain it. Okay, so ACPI is not in our scope right now. Let's get back to WMI and compare it with a simple web service that can turn LED on and off. So I think most of you have some experience with using RESTful APIs, so let's just compare RESTful API and WMI calls so we can get a better understanding of it. Okay, so in a RESTful API, we usually have a domain or an endpoint which you will send your commands or payloads or everything to there. And in WMI, we have something a little different, which is usually called a UUID, which is a unique identifier for a resource or something that's like a namespace. So in our case, for example, the whole Acer gaming function WMI calls will be made to this UUID, which starts with 7A here. And then in a RESTful API, we have a pass and usually a method. And with this, for example, I can set my LED state to on, so I can turn my LED to on. Let's say this is just for an IoT device. And in WMI calls, we have something similar, but usually this is a simple byte. So maybe I will just send 0, which indicates to turn the LED off. And if I send 1, it indicates to turn the LED on. And then you can see that in the RESTful API, we usually use JSON format, but in WMI calls, we are just working with simple bytes. Okay. So, for example, in a RESTful API, I can get the state of a LED by making a request to this URL, which is the get LED state, and the response will be the LED state is off. And then we can use another endpoint to set the LED state. And then if we issue the get LED state again, we can see the LED state is on. Now for WMI calls, we can also do something similar. We can execute the method number 2 in the UUID related to Acer gaming functions, and we can see it returns 0. So what it means is that the LED state is off. Then we can set the LED state using another method, which is method number 4, and it may sometime return a value, and that value may have a meaning to say the operation was successful, or it can also indicate that the new state of LED. And then if we execute method number 2 again, we can see the LED state is on. Here we can see an abstract figure of communication map between application to hardware. For example, in our case, our application is Acer Predator Sense. And here we have the operation system, and with the data flowing between these modules, it will get eventually to the hardware, and then the hardware can connect to the BIOS. So usually our application is outside the operation system layer, or we usually call this the kernel space, and here the application lies in the user space. So the user space can communicate with kernel space. In our case, we are trying to communicate with the kernel space using a custom driver. So that's basically what I did. I added another kernel module as a driver, so my custom application can contact with kernel. Then the kernel can communicate with ACPI driver through the device driver, and then the WMI is, from what I understood, inside on the part of the ACPI driver. So we can use the WMI inside the ACPI, and with calling some ACPI methods, we can communicate with hardware. And that's all I did basically. Okay, so let's move forward. Okay, so in order to implement the missing features of Acer gaming laptops in Linux kernel, we will need three things. One, GeoID. GeoID is something like the namespace, but this is our UUID. So the namespace is some characters like Acer gaming function. So this is some human readable text. But the GUID is in format of a UUID. So this is something the computer can understand better. So the first thing we need is the GUID, and we already found it. The second thing is the method ID. And again, this is not the method name. We need the method ID because, again, the computer can work with it better. And the third thing is that the payload. So you have a namespace, you know what method of this namespace you want to call, but you need some payload and data to send to this method, and then you will get a response. So what we need here is that we need to know what payload should we send and what's the meaning of the response. So again, we already see the GUID in the WMI Explorer. So I will skip discovering method ID to the next video. And for now, we will focus on discovering the payload values. For now, we have a new challenge. In previous video, we found out that there is Acer gaming function namespace. We saw many methods, but we don't know what are the inputs and outputs for these methods. First option is to use a decompiler and figure it out. And so you can use a decompiler and decompile the Acer Predator Sense application and try to understand what each part of code does and what methods are getting called, and you can determine the payload and also the response if needed. The second method is to use a tool to monitor WMI queries. So basic idea is that if you can listen on the WMI calls that are being made with the Predator Sense application, if your monitoring tool is good enough, it can show you what are the inputs and what are the outputs. And the third method is to use a debugger and set a breakpoint at runtime. So if you manage to set a breakpoint either on system calls or breakpoints on some specific lines of codes in the Predator Sense, you may still be able to see what are the values that are being sent. So right now, we don't have access to Acer documentation. So if you're saying these options are the best and most accurate ones, as far as I know, But as a Sigma male, I prefer going the hardware, which is trial and error. So I literally tested every get function in WMI methods by simply checking the difference of WMI function return values before and after changing the keyboard color. After repeating the process over and over again, I realized that the Acer KB backlight return value is changed each time I change the keyboard color. This function returns an array of bytes, and each of these bytes had their own meaning. So let's break them down. And this is actually easier than it looks. So this is the method. Get gaming KB backlight. So whenever you execute this method, which is a get method, not a set method, it will respond with an array of bytes. And you can see that. So as I said, what I understood that is that if I change a keyboard color, I can see the response being changed here. But we don't know what is the meaning of these bytes. So let's try executing some commands in the predator sense by changing a keyboard color or a configuration in keyboard LED animation and see what changes. At first step, so I simply try to execute the method, and the top row is what I got. Then I tried to change the keyboard animation from left to right to right to left. So this is a single change, and I hope that it would only change one byte. With success, we can see that after changing the keyboard animation direction, the only byte that have been changed was this one. Then I tried something else. I tried to work with keyboard LED color. So I tried to change a color from blue to white, and these bytes were changed. So you can clearly see this is 0, this is 0, and this is 255. And with the RGB coloring method, this there means red is 0, green is 0, and blue is at the maximum byte level. So after changing it to white, all the red, green, and blue colors turned into the maximum value. So that we now know these 3 bytes here are responsible for managing the keyboard color. So I repeated this process over and over again with any other configuration I could find at predator sense, and this was what I found. So the first byte was fake modes, and the second one was controlling the speed. And one funny fact about this byte was that in the predator sense, you can change it from 1 to 9, but if you try to play with it manually, you can change it to any value. So if you change, for example, the speed to 0, the animation will freeze, and if you give it a speed more than 10, the animation will be super fast. So maybe this is not something recommended, and maybe it can damage the computer. So let's make sure you don't play with these values a lot. And there were also some bytes that I didn't know, like the byte number 3. And I couldn't find any meaning for it. Maybe this was related to some features that my laptop didn't support, and maybe it was reserved, and also maybe it's a corner case that I didn't find out any information about it. Okay guys, so that's it for today's video, and I believe with these methods, you can work on understanding your other missing features in your laptops, and hopefully you can also contribute to the project so all the users can use all the features they're missing in their Linux setups. See you!